Here's another question involving magnetism. A teacher used the equipment shown in the figure below to demonstrate the motor effect. So we can see here we have a circuit involving a copper rod, and around the rod we have a horseshoe magnet. So the question is, describe how Fleming's left-hand rule can be used to determine the direction in which the rod will move when the switch is closed, and state the direction. Okay, so if you look over here, when we close the switch, now our battery can create a current flowing through the circuit. The current always goes from minus to plus. In the rod, the current is going to be going in this direction. So we have a current in the rod, and we also have a magnetic field pointing north to south. We know that when DC conditions arise, when you have a current flowing through a metal wire, or a rod in this case, and a magnetic field, then they will interact and create a force. That force will then cause the wire to move, and we can use Fleming's left-hand rule to work out which way it goes. So remember, first finger points north to south. The second finger is going to point from plus to minus. So we're going to rotate our hand slightly inwards. There we go. And now we can see that the middle finger is pointing from plus to minus, and the first finger is pointing from north to south. In this orientation, the thumb is pointing upwards. So how do we describe this? We're going to say that the thumb, index finger, and middle finger are held 90 degrees to each other, or at right angles. That's one mark. Then the index finger points from North Pole to the South Pole. That's a second mark. The middle finger points from the positive side of the current to the negative side of the current. That's the third mark. And finally, the thumb will show the direction of the force. That is the fourth mark. In this case, the rod moves up. That's an extra mark. Okay, increasing the current can increase the force acting on the copper rod. Give one other way in which the size of the force can be increased. So we know that for the motor effect, force is equal to magnetic flux density times current times length. Or we can just call this Bill's equation. By the way, Bill's not a real person. F stands for force, B is the magnetic field of the permanent magnets, I is the strength of the current, and L is the length of the wire. So they've already increased the current. What else could we increase? We could increase the magnetic field, or we could increase the length of the wire. Okay, part C. The copper rod has a length of 7 centimeters and a mass of 4 times 10 to the power of minus 4 kilograms. When there's a current of 1.12 amps, the resultant force is 0 newtons. Calculate the magnetic flux density. Okay, so we want to work out the magnetic flux density. That means we're going to rearrange Bill's equation, and that's going to give us B equals F over I times L. Now they haven't given us the force, however they have given us mass. And we know that weight is equal to mass times gravity. Weight is an example of a force, so we can put that there. The current is also 1.12, and the length of the wire is 7 centimeters. So first of all, let's find out the weight. We're going to do mass times gravity. That gives us 3.92 times 10 to the power of minus 3n. The length is 7 centimeters, however it has to be in meters for this equation. So that becomes 0.07 meters. We already know the current is 1.12, and that's in amps, so we can leave it as it is. Plugging in the values gives us the following, and the answer is 0.05. So the magnetic flux density is going to be 0.05. Now the units for magnetic field is T. T for Tesla, not Toyota. Hey guys, if that video helped you, support our channel by liking, subscribing, and sharing it with your friends. And more importantly, if you still have questions, drop a post on our forum at ExamQA.com, where I will personally be there to help answer your questions. Mohammed signing out.